We present DiffCloud, real-to-sim from point clouds with differentiable simulation and rendering of deformable objects. First, we will describe DiffCloud inputs. Our hardware setup consists of a Canova robot and two RealSense cameras, one mounted on the side and one overhead. Next, we manipulate deformable objects and record point clouds from both views. Using knowledge of the geometry, kinematics, and meshes of the Canova robot, we also mask out the robot from point cloud frames such that only the deformable object is captured. The merged point clouds serve as input to DiffCloud. The goal is to estimate unknown physical parameters of the object, such as stiffness and mass. We use a mesh-based deformable simulator. In simulation, we execute the same trajectory on the deformable object which was performed on the real robot, resulting in a deformed state. From this state, we differentiably sample a point cloud from the surface of the mesh. Next, we take the loss incurred between the simulated and real point clouds. Since the simulator and the point cloud sampling procedure are both fully differentiable, we can propagate the gradients to the estimated simulated parameters and perform updates. We repeat these two steps until point cloud alignment is achieved, indicating that we have found simulated physical parameters that fit the observed real point clouds. We evaluate DiffCloud on two real scenarios, starting with lifting a cloth off a table. We show the real point clouds for a stiff, lightweight paper towel and a heavy, collapsible polka dot patterned cloth. On the left is the target input point cloud sequence, and on the right is the result of visualizing the simulated cloth with the parameters found by DiffCloud as point clouds. We find that the inferred parameters produce point cloud alignment between real and sim, noting that DiffCloud correctly learns the shape retention and self-collapse behaviors of the paper towel and polka cloths. Next, we move on to fold. Similarly, we show the trajectories for two cloths of very different properties. We note that the fold scenario exhibits a high degree of self-occlusion and partial observability. Nearly half the cloth is not apparent in the point cloud due to the resting half of the cloth being indistinguishable from the table surface. Still, DiffCloud finds parameters that fit the observed trajectories and learns the shape retention versus self-collapse properties. We also evaluate DiffCloud on two simulated scenarios using synthetic data as input, band stretch and vest hang. In these experiments, we will visualize the initial guess for parameters that DiffCloud starts from in black, and compare this against the final optimized parameters in blue. Two target sequences for band stretch are shown in green, where varying the band properties affects distance traveled upward along the pole. DiffCloud successfully finds these parameters, shown in the blue column. On the right, we see that DiffCloud starts from an initial guess for parameters shown in black, which diverges from the target behavior in green, but eventually converges to optimized parameters in blue, resulting in alignment with the target. For vest hang, we show a highly deformable and shape-retaining vest, with the properties affecting the resting pose of the vest on the pole. DiffCloud learns to infer parameters that describe these behaviors. Thank you so much for listening, and for more information, please feel free to check out our website or stop by our poster session later today.